I'd like to welcome everybody to this presentation on uniform hashing of arbitrary input into key exclusive segments. Rather complicated title, but what we're going to talk about is partitioning your data into independent segments. This is a joint effort by both Paul Dorfman and I. It is some things that we learned as a byproduct of working on our SASPress book, Data Management Solutions Using SAS Hash Table Operations, a business intelligence case study. So let's talk about what the problem is. Our problem is we've got way more data than we've got resources to handle it. There's a number of solutions for that. The first solution that virtually everybody goes after is let's go get more resources. So you request more resources, and if it's not enough, you go back and you request more, and you keep on doing that until somebody says, nah, we're not giving you any more resources, or you've reached the limit. An alternative approach is what we're going to refer to as divide and conquer, where we want to divide the data into a number of smaller chunks, process each of those segments individually, and then as we complete creating our output, we're going to add that output to a cumulative result so that at the end we have our final result. The divide and conquer approach is what we're going to focus on in this presentation today. So, once again, our problem is our input is too large to aggregate the data in a single pass. So the first question you would ask is, well, can we do it in multiple passes? Can we do it in pieces, if you will? So here's a very simple SQL query where we're saying, I want to select the field ID key. I want to do some aggregates on our analytical variables. We're just using var here as a placeholder. We're going to focus on aggregation in this presentation. However, the techniques that we're going to talk about apply to virtually any other data management task you can think of, like joining tables, sorting tables, etc. I do want to point out that one of the issues that we've dealt with in this approach is the problem of doing account distinct. Account distinct is not something that you can do in pieces and then re-aggregate the results. Like if you want to calculate a mean, you can break up your data into chunks, calculate the sum, calculate the count of observations, and then re-aggregate once you've got a smaller set of data. That doesn't work when you want to do a count distinct. So the criteria for what we need to do, we need what we call key independent segments. An absolute requirement for that is we can't have any key value in more than one segment. So you can't have a key value in one segment that's also in another one. So think of the combinations of our variables ID and key. A desired, although not absolutely required, feature is that we would like to have a way to roughly evenly divide the data into those chunks. So once again, there's multiple ways to do this. One way is, perhaps you have a priori knowledge, or the business users have a priori knowledge of the data, so you can get that information from them. But the problem with that is you then have to validate it. You can't necessarily always assume that things that users think about their data is actually correct. An alternative approach is to map the segments via a hash function, and that's what we're going to talk about in this presentation. So the idea is, as some background, our composite key values are very diverse, very numerous, but there is going to be some combination, as we say here, of their bits and bytes that can be used to split them up into distinct or discrete groups. The problem is we don't know what that combination is or what the formula is. So once again, we'd have to try to figure it out. The bottom line, however, is we don't need to know that. That's where the SAS hash functions come into play. We're going to create a string variable, a character variable in SAS terminology, called H key in such a way that the combination of values is highly random, and each unique combination of values maps to one and only one value of H key. We can then use that value to break up our data into smaller chunks. So let's look at some simple code to do this. We're going to use the catx function in SAS. The catx function says concatenate the values of ID and key, strip off leading and trailing blanks, and then separate them with, in this case, a colon. I want to emphasize that it's very important that we use the catx function and not the catS function. We're then going to use that as the argument to the MD5 hash function to create our H key variable. We can also just nest the functions directly, as you see here. We'll talk at the end of the presentation about an alternative hash function, SHA-256. So here's our sample data, 15 rows, because that's all we could fit on the slide. So what we want to do here is demonstrate the distinct key values, and we're going to create what we call a map table, which is all the distinct values of ID and key. And notice we've got our, once again, our nested function. The MD5 creates a binary string of length 16, and we're going to use the hex 32 format so we can actually look at the data values for it. Now, let me also state that this table, the map, which we may want to keep, we could make that a view instead of a table. We could also use views for when we have to add this field to our source data. That can be particularly important if our data sources are particularly big. So here's our test table, our results, and notice that whichever set of two characters, if you look down the columns, there are no overlaps. In other words, 1A, D6, 8E, 0E, B3, 1E. In other words, we could use these six, just this position, to partition our data into 6 groups. Likewise, combinations, no matter which position we pick, 1, 2, 3, we're going to get a random distribution of mutually exclusive values. Now, the next part of that is we don't necessarily want to use 6 groups. We may want fewer groups. And if we've got lots and lots of groups, we obviously don't want to have to process the data for each group. So that's where we're going to want to convert that signature byte, in this case, byte 10. So if we go back, byte 10 is over here. So we're going to use that byte. And we can use the char function, or we can use the rank function. If we use the rank function, we can then assign a segment value. So if we've got 487 different values of our key combinations, but we want 4 groups, we could use a formula like this, and it will give us a value for the variable segment between 1 and 4 that will combine some of those individual groups together. So here's our segmentation picture for our file trans. So you can see that it combined some of the groups. So we've got 6 groups, but 3 segments. So we're going to process segment 1 together. We're going to process segment 2 together, and segment 3 together. So here's our sample macro brought all together. I'm going to leave it to the attendees, the virtual attendees here, to research this on their own to verify that the code actually works. But I'm going to just make a few observations about this code. The first thing that we notice, we've got this very long string, which is doing the MD5, just like we saw before, and then we're doing the rank of that and then the mod. So we're going to get a value of X that ranges from 1 to whatever the number of segments are that we want. If we then look at our proc-SQL code, we're doing an aggregation, and note that we're using as our aggregation keys the original source values. So those are still part of the data, but notice in our where clause, we're using the segment value to subset the data. So each time through this loop, we're going to process one segment, and we're going to accumulate the results using proc append by appending it to the name of the data set we specified as our output. So here are our aggregation results. On the left-hand side, this area in blue, these are the results that we would get if we were able to process it, as we call it, straight through without any segmentation, whereas the yellow area over here is where our segmented results. Notice the order is different because it's sorted by our segment number, which basically combined A2 and B1. But if you look at the results, they are exactly the same, which is what we want. We want to have the same results. Now, I know what you're probably saying, and actually the first time Paul told me this, when he thought of this idea, I said, you got to convince me because I'm not sure I believe it. So what we did a lot of research, and so here's just a sample where we're going to create a lot of key combinations. So you can, type in this code if you want and do the same thing. We're going to say, I want to create 4 ID values. This is going to give us 1,000 values of the variable key. If we wanted to make it 1,000,000 zeros, we could just add 3 more zeros in here. And we go through and we create our H key, our rank, and our segment, and our output. And if we do that, we're going to discover we've got mutually exclusive groups. And notice, per one of our original requirements, if we wanted approximately equally sized groups, if we run this with and ask for 3 segments, the count and the percent is roughly a third. If we run it with 4 segments, the counts and the percents are roughly a quarter, or 25%. So we've been able to partition our data into different segments that we can process independently of one another without having to know, frankly, anything at all about our data. So in our particular example that we've used so far, as I said, we've been using SQL as our aggregation method. The technique that we're talking about here is going to apply to any aggregation method you can think of, such as what we call sort control break, which is basically doing a proc sort in a data step, perhaps with a by group processing. The SAS hash object, and let's not confuse the SAS hash object with hash functions. They are separate things. The means procedure, the summary procedure, univariate, etc. You name it. So we would just, thinking back to the macro that we saw before, we could just replace the proc-SQL step there with a proc sort that looked like this, and then do our by group processing to do our aggregation. And I'd also like to point out that in a sort control break solution, we can take advantage of first dot and last dot variables. Notice that we sorted the data by both our keys to identify, or our class variables to identify our group, and the variable var. So now first dot var is only going to have the value of 1 on the first observation in each group of data. So that allows us to do a count distinct. Now, this concept of key independent uniform segmentation works regardless of the nature of the data, regardless of the industry. It really, really does not matter. On projects that Paul and I have worked on in the past, we've used this on point of sale retail data for a project for a large grocery store, and think about the amount of data that they have, where every item that somebody purchases in any store is going to show up as an individual observation. We've also used it for financial transaction, insurance claim data, and I'm sure somebody is using comparable techniques, for example, with Social Security data. Probably the classic example of a large data source. So when we go through this process, however, one thing that's particularly important is making sure to pick an appropriate number of segments, because we're going to have to process each segment of data separately, which could have other impacts. So you want to make that choice judiciously. That's going to be something that where you are going to have to look at what kind of resources you have available to you, how long you have, the nature of the data. So that's going to be something that you are going to have to take some business knowledge to do. The second part is you can use a single byte from the H-key value that we saw before. For example, if we just pick H-key byte 1, that's going to allow for up to a 256-way split, because remember that was a hex value. So there are those values range from 0 to 255. A W of 2 gives us 65,536. We're probably never going to need nearly that many, but for all practical purposes, probably 1 or 2 are going to always be more than sufficient. But I guess you could go up to as many as 4 if you needed to. We'd also suggest, based on experience, that the N value you choose be a power of 2, because that's going to help keep the partitioning of the data into equally sized groups the same. And that's where the mod formula comes into play for us. Now, the other important thing to ensure is to make sure that when we create the H-key mapping, that it does accurately correspond to a one-to-one relationship between the input data. And there are 2 stages to that, as it says here. One is concatenating all the process components together, and the other one is making the H-key unique. Let's take each of these in turn. So for the concatenation uniqueness issue, as I mentioned at the beginning, when I showed you the catx function, I said it's particularly important that you use the catx function, because that's how you're going to delimit values to make sure they are distinct. So there are 2 issues to pay attention to there. One is the default buffer length that the catx function uses. Catx is going to create a character variable. If the combined length of your keys is longer than 200, it could truncate them. That could cause problems. So make sure to use a length statement if you need to. The other is you could improperly use catx delimiting. So that's why I said, once again, use catx. And you also want to make sure to use a different delimiter from any value that could be in an endpoint of an individual data value. So the next step of the hash function uniqueness process is the MD5 function has a theoretical vulnerability that it is theoretically possible that it could map 2 different arguments, 2 different combinations of values to the same signature, i.e. H-key value. However, there's only a 50% chance of getting one such collision is 200 quintillion distinct arguments. I know a lot of people have a lot of data, but I doubt we're ever going to hit that. Another way to think of this is you would have to execute this function 100 trillion times per second for 100 years to get a collision. So for all practical purposes, you're never going to have an MD5 collision. However, if you want to make sure that that can never happen, maybe your life is on the line, for example, you could use the SHA-256 function. Recall I mentioned that earlier when I mentioned the MD5 function. It has no known collisions. So there's no chance, virtually no chance of a collision. The problem with the SHA 256 is it's much slower than the MD5 function. However, if you're only doing if you're only doing the hash assignment once, as opposed to the significant time you're spending processing your data, that's perhaps a small price to pay. Well, with that, I want to thank you for your attention. Paul and I would both like to thank you. You can reach us at either of at these email addresses, or I'd also like to suggest that a better way to ask us questions about this is to post a question on communities.sas.com and tag either or both of us. Paul is known as @Hashman. I'm known as @DonH. And the advantage of using communities.sas.com is that others can also chime in, and others can also benefit from your knowledge, your question, and your experience. So once again, thank you for your attention.